I'm going to show how to transpile a diagram to running Python code. I think this can be done for other languages. I've done it for Common Lisp, I've done it for Bash. I imagine JavaScript is just as easy, and so on. For this simple example, I'm going to start with something painfully simple called hello world.draw.io. I'm going to use a tool called draw.io or diagrams.net for editing diagrams. It has its own format, but what I really want are the four essential ingredients of SVG, which are rectangles, ellipses, lines, and text. The generated code in this case is going to go to a file called top.py, and we're going to be able to run that code. And then I'm going to talk about how to read the diagram and how I built a script called run.bash to do this. Installing and running d2py, which converts Python drawings to Python programs. So we'll go to 10, create a working directory. You can do this in your own directory. And then I've written a bash script to do the work, since you don't want to watch me mistype this stuff. So /git.bash. So now it's pulling the stuff down. It's done. We'll clear the screen, cd to the Python diagram to Python directory. We'll run make, which should build the various intermediate programs that we need. I called them layers in this particular case, in this proof of concept. Then it runs the program, which is what's happening now, and it's finished. Now we run the resultant Python, and we get this. Example, I'm going to build an app called Hello World. It contains two components. Components are asynchronous by default. That means they run at any time and in any order. Components have inputs and they have outputs. Inputs are green circles, outputs are yellow circles, and I've used draw.io to deposit text A into this input, and I've called this output out. Red boxes are used for defining synchronous blobs of code. In this case, I put Python in this piece of code, and down here I put more Python in, and then lines, arrows are show message flows. So a message flows from here to here, then a message flows from here to here whenever this component calls the send routine. We create two components called hello and another one called world. We put Python code inside the components. We string the components together using an arrow. The arrow flows from hello.out to world.in. The whole app is called Hello World. When we send the message to hello world.start, the message goes from the go input of hello world to the A input of hello. That fires this code. The code prints hello, and then it calls send, and it outputs true to its out pin, its out port. and that sends a message to here. The world component wakes up, then it immediately calls print world. It ignores whatever input came in, and it doesn't produce any more output. And so the app finally finishes at this point. Now we're going to look at this app in layers. Let's scroll down to here. So the topmost layer is the component called Hello World, and it has one input pin. We go a little bit deeper in and we see that Hello World contains two components. The Hello component contains an A input and an output. And the World component has one input called in. We go a little bit further and we look inside of Hello and we see that it has a block of Python code. We look inside of World and we see it has another block of Python code. And then we look at the message routing, and the messages are these arrows. One arrow goes from go to A and another arrow goes from out to in. We'll note that the routing is not controlled by the children, so Hello can't immediately send a message to World. The routing is owned by the parent component called Hello World. So when Hello wants to send a message to out, it asks it, parent, please send this message. It puts the message on out. The parent then says, oh, that out pin is wired to this in pin of World, and it takes that message and moves it to here, and then it says, wake up World. And World wakes up and runs its own code at that point. And then there's no more messages in this simple example. We're going to look at the way the script run.bash is built up. We're going to start with just a diagram overview, and then we'll look at the code later. In this diagram, we'll note that there's green inputs. We just send a string into we call real path in this particular case. And in my particular case, it was I wanted it to expand this squiggly thing into a full-blown path name as a string, and then that string gets pushed into this input. And then we take another string, which is the name of the file that we want to compile, in this case hello world.draw.io, and we push it into this input. These purple inputs are other scripts. So the bottommost script is d2f.com. Above that is dos2f.com. DOS means diagrams as syntax, and F means fact base. And then we go even higher up and we go from diagram to factbase.com, and we push that in here. This purple rectangle runs these scripts with these inputs, and it produces an output JSON file onto this grayed out database drawing component. We then run a piece of Python code. In this case, I called it emit.py, and it generates 4 files: hello.py, world.py, hello world.py, and top.py. And there's no actual outputs. Well, the outputs are these files, and those are synchronous outputs. So they only appear when this thing gets run. There are no asynchronous outputs in this particular piece of code. The arrows on this diagram are what I call ducts. If we were writing bash code, we'd say they're probably pipes. And if we were writing Python code or JavaScript code or HTML code, we might use sockets in those cases. Sometimes we might try to implement ducts as function calls, but we can't always do that because function calls are synchronous and ducts are not synchronous, and components are not synchronous. They're asynchronous. I tried to discuss this issue in a blog article that I called Call Return Spaghetti. I try to show there how to chop up function calls into 2 parts: the sending of data and the invoking of of a function. And you can read that to get a better idea of how to chop this up, and you'll actually see that happening in the other Python bits of code. mpos.py and dispatcher.py implements basically what call return spaghetti talks about. Code that implements that diagram we just saw. The first thing the bash code does is it creates the ducts. It gives them random names, and then it implements them as FIFOs, which are named pipes in bash. It also creates a variable called root. It does this with this kind of bash syntax, which denotes the directory immediately above us. Here's the line that does the real work. It invokes this dash DAS diagrams to sit as syntax to py.component, and it assigns the ducts to the appropriate inputs of that component. So there's, I think, 5 inputs, and I chose to use 3, 4, 5, and 6 as the input file FDs, file descriptors. If you know bash and Unix, then you know what I just said. Otherwise, don't worry about it. I avoid 0, 1, and 2 because those are hardwired to mean other things in bash. And most notably, I have to use an ampersand here to spin this component off as an asynchronous component. Bash comes with rendezvous hardwired into it, and we don't always want rendezvous. In fact, when implementing asynchronous components, we never want rendezvous. This part down here sends those strings that we got up above into the various ducts, and then we finally wait for the component to run, and Linux will decide when it runs. Linux or Mac OS or whatever you're using will decide when to run that component. It'll run that component, it will give these inputs to the inputs of the component, and then the component will produce some sort of output. In this particular case, it creates 4 files and writes to them, and when it's finished, it dies, and then this wait instruction is satisfied, and then we just do various bits of cleanup, and then we actually run the final code, which is in top.py, and then we got some informative messages here for the proof of concept. The source code for the files is listed in this README file in this directory here. There's a script here to download each of the files, pull each of the files. You want to look at the README file. If you use Obsidian, I wrote the README in Obsidian. It might make it easier to read. And 3 files. There's mpos.py, mpos.py and dispatcher.py, and those are both implemented manually at the moment. mpos implements the classes required to implement components, and dispatcher actually implements the multitasking between components. And you'll see that it's a much simpler multitasker than, say, a full-blown Linux or Windows or Mac OS.